Everyone. Today we are pleased to welcome Francesco Cremonesi from the French National Institute for Research in Digital Science and Technology in France. Francesco is a research engineer in data science and machine learning with a focus on privacy-preserving approaches such as federated learning, particularly in sensitive domains like healthcare. In today's talk and gentle introduction to federated learning, he will introduce the key concepts and explain how federated learning enables collaborative analysis while keeping data secure. And with this, I give the floor to Francesco. Thank you, Francesco.
Okay, thank you very much, Sotirula. Thank you, everybody, for joining today. So as Sotirula said, today is going to be a gentle introduction. There will be a little bit of algorithms and math, but I will keep that to a minimum. And my goal today is to make sure that at the end of the presentation, you're able to answer the question of like, what is good and what doesn't work so well with federated learning? Which situations can I apply federated learning? And is federated learning potentially for me or not? So if you're getting confused by the end of the presentation and this is not clear, please stop me at any point. And this is really the goal for today. Oh, sorry, now we'll go into maybe presentation mode. Okay, so to give you a little bit of the context for federated learning. Basically, the first thing that we need to place on the map is the fact that we want to move a little bit from, let's say, classical statistics, population level statistics, to what we call sometimes precision medicine, personalized medicine. So we want to basically be able to make predictions about a specific patient and not just, describing the population in general. And so for this, to achieve this goal, we turn to methods that are more taken from machine learning or deep learning, let's say, fields, rather than, as I said before, classical statistics. And so the idea really is to revisit old problems, like predicting treatment response or prognosis and so on, in the light of these novel learning approaches that offer a more personalized solutions. But to achieve this goal, we need something that was maybe still needed for classical statistics, but maybe not so much, which is we need very good, large, diverse data sets. So obviously, good data is necessary in general for making, good analysis. But machine learning specifically, and deep learning even more so, is known to be very data hungry. So this is really a challenge that arises when we move toward learning style of approaches. And then specifically, obviously, in the context of the Helios action and other types of actions that are focusing on rare diseases, it's pretty clear that no single center, they may be quite big even internationally, but rare diseases are so rare that sometimes not even a single center will have enough data to reliably feed a machine learning or a deep learning model. And so for this, collaboration is essential, even more so than in classical medicine, even though, even for classical medicine, we need a lot of good data if you want to apply machine learning. But the problem that we are facing is that data sharing is not easy at all. And I'm, of course, talking about, regulations, privacy, and so on. But I'm also talking more broadly about, there's a lack of incentives for data sharing. There's some institutional barriers. There's many technical barriers that make sharing complicated or cumbersome. And so basically, this is kind of setting up the context that when we talk about federated learning, we basically need kind of two preconditions. One is we want to do some type of learning, so machine learning or deep learning or whatever. So we want to apply these kind of statistical methods that involve learning from large amounts of data. And secondly, we are in a collaborative setting. And I guess thirdly, data sharing is difficult, but this is kind of happens all the time anyway. And then specifically for when we talk about rare hemoglobinopathies, so we're in the Helios cost action, and I'm not an expert, so I'm talking a little bit here. So please correct me if I'm saying something particularly stupid, but there's issues such as geographic fragmentation. So there's a lot of heterogeneity among different areas in Europe and even within, I guess, the same country. This could be. The diseases themselves are very heterogeneous. So there's a lot of variation in the way that the disease arises, in the kind of genomic profile and so on. And because of all this heterogeneity, there's historically also been big differences in diagnostic practices. I know that other working groups in Helios are working to kind of promote standards and guidelines for diagnosis. So this kind of shows how diverse the landscape is right now. And as I said before, we have barriers to data sharing, such as GDPR and other issues. Even though when you speak to the researchers and to the research centers, many would be actually happy and willing to collaborate, specifically via federated approach, and we'll explain what this means later on. So the Helios action has been instrumental in kind of describing the situation, both with the guidelines and the sort of analysis of the diagnostic practices that is being done by other groups. And on our side, in the working group 3, we've been doing some, we sent out a survey to map the willingness to collaborate and the readiness to collaborate as assessed by FAIR principles and so on. And so the idea of federated learning falls naturally into place in this context of very heterogeneous, very complex diseases, where every country is, following maybe some international guidelines, but also doing something kind of locally different from the others, and so on. So, what does it mean to have a scientific collaboration, data-driven collaboration that is privacy preserving? So the step 0 that we need to talk about involves data anonymization. So one way that you can share your data with other researchers is simply by making it anonymous. And anonymous means that you have sort of coaxed and coerced your data so much that at the end of the day, it is impossible to trace back individual samples to their original data subjects, basically. But there's a huge trade-off in this process of anonymization, which is that the more privacy you wish to enforce, the more you are destroying information in a way. And so, for example, you may be, instead of specifying the exact age, you may be giving an age bucket, and you may be removing some essential information. Okay, the example here is removing the email. It's not maybe an essential information for hemoglobinopathies, but you get the idea. And rare diseases specifically are so difficult to anonymize because since they are very diverse and very rare, almost everybody has a slightly different version of the disease. And so just by looking at the data, it's very possible, it's very easy to go back and trace back to who was the actual subject of that data point. Okay, so data anonymization is not always feasible, nor is it something that could be desirable. Maybe you think that data anonymization is destroying too much information. And so comes the idea of federated approaches and federated learning in particular. And the slogan for federated learning is move the algorithm, not the data. So in this example here, you have different data providers with their computers and their whatever databases on the top. And basically the idea of federated learning is, instead of asking these data providers to give me their data, I, as a data scientist, will give them my algorithm or my model, and they will run it locally. And then through some sort of, well, magic for now, but I'll explain later on why it's not magic. Through some sort of manipulation, I will be able to aggregate all of the different responses that I get from each data provider into a unified response that includes all of the information from the different data centers, even though none of them, the data for every center has never left their site. So this is kind of the idea. The data always remains on the site where it is generated and protected. And the thing that moves around is the model or the algorithm, and we will see in a few minutes what that means in practice. Okay, so if we were to characterize federated learning in a bit of a more formal way, it's part of the family of distributed learning approaches because the learning is being done by each center in a distributed way. They can do it in parallel, they can do it asynchronously, it doesn't matter. But everyone does their own thing locally. And the idea of federated learning is that we are never sharing the raw data, but we are still able to collaboratively train some machine learning or deep learning model. And so obviously, the key challenge that federated learning was born out of is privacy preservation. So really, we always thought privacy preserving as the main benefit of federated learning, but there are other sort of ideas that we can throw around a little bit. For example, this idea that it's really easy to plug in new centers and to involve them in your collaboration and to have this shared training of the model can help in increasing the diversity and the inclusivity of your final model. Because it's so easy to scale up to including new centers, there's also this idea that it's easier to have more and more data, so scalability. And something that I have to say, because it's often cited in the literature, but I think it kind of should come with some caveats, is we sometimes say that federated learning can reduce the communication cost. This is especially true if you have very big data sets, like imaging maybe data sets, and smaller models. Because since as we said, the thing that's moving around is the model, the algorithm, and not the data. If your data was very big in terms of gigabytes and your model is very, very small, then you are saving some communication. Okay, and so I want to, before I dive in a little bit into explaining kind of the landscape of what federated learning can look like and what are the specific algorithms and so on, I wanted to have this basically a small slide to demystify a little bit federated learning. So imagine that you have this very simple example that you want to compute the average age of these people at different hospitals, but you never want to share their data. So the data that you don't share is in gray here. And basically what you do is that instead of just simply computing the average age per hospital, you would compute, okay, the average age, but also the total number of subjects in that, or of patients in that hospital, in that center. And then you share these two information with a centralized server who is then going to be able to compute simply a weighted mean of the different results that he got to have the exact average age at the end. So I think, to me, this example is informative because, first of all, it shows that you can obtain the exact same result that you would obtain by centralizing the data, even though you've never shared the actual data points. So this is kind of the key point of federated learning, to be able to obtain exactly the same answer or as close as possible to the answer that we would have by pooling all of the data together, but we've never shared this data. So to be clear, the sort of the entity, red entity in the middle, who's computing the final age, they reach the information of what is the average age, which is what they wanted to obtain, but they have never ever seen the, John's age or Alice's age and so on. So this is the important point. So this is number one. Number two, this example shows that you have to play around a little bit with your algorithms in order to obtain their federated version. So in this case, for computing the average age, it wasn't sufficient to just compute the average age at every single hospital, but you also had to compute the count. Okay, then we will see some more complex cases later on. The third informative thing about this example is that it shows that the information that each hospital shares with the final sort of central server is aggregate information. So every hospital only shared the average age and the total count. And in, let's say, step 0 of privacy preservation, this is the minimum that you need in order to claim that you are at least trying to preserve the privacy, because we are only sharing aggregate level quantities and never sample level quantities. And finally, this example introduces a little bit of a challenge that will become more apparent later on. So if you look at the distribution of ages here, you see that there's kind of some hospitals where you have more adults kind of distributions with maybe some geriatric, and then one hospital with only sort of ages on the pediatric side. And for this specific algorithm, it doesn't matter, but in general, it kind of shows that federated learning often has to deal with very heterogeneous distributions among the different hospitals. And for more advanced algorithms, this is actually one of the big challenges that we have to face. Okay, but overall, the point of this slide is to show how federated learning is nothing more than sort of a few mathematical tricks in order to achieve this very important goal of never sharing the sample level data from the hospital. Okay, and so to give you a little bit of an idea of what federated learning can mean, we often distinguish in the literature between two flavors of federated learning. We have the cross-device, where we're really thinking about maybe millions of people that are collaboratively sharing their models in order to have a huge, mega, sort of super intelligent model at the end. But we're talking about millions of people, and so typically the hardware that they use is really like, phones, smartphones, or wearables, not very powerful devices. And this is actually the context where federated learning was born, because the initial, let's say, public experiments that we know of were done by Google for their keyboard. So the thing that predicts the next word that you're going to type on your keyboard is actually a model that is trained in a federated way. And this was kind of the main motivating example for Google to develop this line of research. And then, so this is the cross device. But then in the medical field, we typically focus more on the cross silo flavor of federated learning. And in this case, we're talking about small numbers of collaborators. Maybe we're talking 3, 10, 100, but not millions. But on the other hand, we're talking about more complex data, more complex models. Typically, something that's in the whatever. If we're talking about medicine, we're talking about lots of data points, maybe about certain patients, genomics, and complicated models, and so on. And so keep in mind that from now on, I will be mostly talking about cross-silo federated learning, even though the literature, I would say, is actually split, maybe 50-50 among the two. But typically, when we're talking about medical data, it's most of the time it's cross-silo. And then another important distinction that we need to make is how the data is partitioned. And 99.9% of the time, when we talk about federated learning, we're thinking of the first example here of horizontal partitioning, where basically you have different subjects at different hospitals, but for every subject for every subject at every hospital, you have the full set of data descriptors, let's say, of data features. So basically, if you've decided to use, the imaging data and the clinical data and the genomic data for your machine learning model, then all of the hospitals that are collaborating in your federated learning session will have all three types of data, but the underlying subjects will be different people. And then 0.1% of the time, we are also interested in vertical data partitioning, where it's actually a much more complicated challenge, where you have the data of one subject is distributed among different institutions. So for example, you could have a genomics lab which only has the genomic data about, Francesco, and the hospital who has the clinical and the imaging data for myself. And maybe these two institutions don't want to share the raw data, and so they need to collaborate in a federated way. But in this case, it's quite complicated to orchestrate a federated learning scenario, although there are obviously, methods and approaches that can be done. And when I say 99% of the time it's horizontal, it's not a sort of a judgment on the importance of each one. It's simply that historically, horizontal partitioning is so widespread that the amount of research and literature that's been devoted to it is quite large. Okay, and then the one last thing that I want to quickly touch with you is that I talked about federated learning, which is, as I said, has this learning keyword inside. So it's applying some sort of learning method in a federated way. But there's a let's say, broader concept of federated analysis and an orthogonal concept of federated analytics. And federated analytics is the idea of doing everything else that's not federated learning, but that is still part of data science in a federated way. So it's about, computing population statistics, doing hypothesis testing, doing data standardization, building visualizations, exploring the data, and so on. And so we are not going to talk too much about this today, but it's important to remember that this is also kind of a very big part of science in general. And there are federated versions of many different well-known algorithms that are typically used for analytics, even though sometimes they can be quite difficult to implement. And especially during COVID, there was a huge sort of burst of publications on federated analytics platforms. So these websites where different hospitals would connect to the same sort of database and allow the federated analytics to build visualizations on top of each hospital's data without ever actually sharing the data, but simply computing the statistics for the visualizations in a federated way. Okay, so let me check on time. Okay. So this is, until now, we've talked about, in general, about the landscape of what federated learning can look like. And now I have a few slides on how it works in practice with the algorithm, and then we'll go back to more general discussions about the pros and cons, and about the different, let's say, applications that are known to me. So I might go a bit quickly here because I think maybe today is not the most interesting for you, but if you are interested specifically in the math, the algorithm side, please get in touch with me later, and I'd be happy to sort of give some more material with you. So just a quick reminder, because otherwise it will be impossible to understand. When we talk about learning approaches like machine learning, we are really talking about something that's called mathematical optimization. And the goal here is really to take a set of inputs and predict some target value. And so these predictions have the benefit of being specific to the inputs that you gave. So if you gave the inputs for one patient, you will have a prediction that's personalized for that patient. So you're not trying to learn something about the whole population. You're really focusing on the single subjects. And the way that learning happens is by, as I said, optimization and providing a feedback signal. So basically, what happens is you start by collecting your input data, which have to be converted to numbers, okay? And then each dimension, so if it's a table, it will be each column of this table. When sort of in the jargon, we call them features. So you collect a bunch of features about all of the samples that you want to include in your data set. And this will constitute the input to your learning process. And then again, you have a sort of something that's called a model, which is basically a black box that takes this input and it outputs a prediction. And the important thing to know is that this model, so this kind of machine, this mathematical formula that takes the inputs and gives you a prediction, can be described by a set of numeric parameters. So you can literally put them in a big list, 0.35, 1.7, and this huge list is a full, complete description of your mathematical formula that allows you to go from inputs to prediction. And this is important because these numbers can be tweaked and changed a little bit. So every time you make a mistake, for every time your model makes a mistake on one specific sample, you can tell it, look, you've made a mistake here, and through some mathematical formulas, you are able to compute precisely how to change those numbers in order to get a better prediction if you were to try again immediately after. Okay, so these are what's called the forward pass, where you make the prediction, and the backward pass, where you tweak your numbers a little bit. And so when in federated learning, when I say that it's the algorithm or it's the model that is shared, I mean that we share this list of parameters. And that's why we can claim that it's privacy preserving, because the list of parameters describes the model, but it's not a description of an individual data sample, even though we will see that this may be not entirely true. And it's an optimization problem because you have to, again, define something that's called a loss function, which is a mathematical formula that basically allows you to quantify how much error you make when you make a mistake, or how correct you were when you were correct. So there's this notion of confidence a little bit. Like if you are correct, but with low confidence, then you still want to push your model in order to be correct with more confidence. Okay? And so learning means simply attempting to minimize this loss function that you've described, because it means that you are minimizing the overall error that you're making. And so federated averaging takes this idea and brings it to the federated world. And okay, let's forget the math. The idea is we will start with a central server who initializes a model. So remember this long list of parameters that I talked about. And the initialization can be completely random. So it will just be, a bunch of random numbers. And this bunch of let's say, model parameters that initially are fully random will be distributed to all of the different hospitals, clients, nodes, however you want to call them. And then crucially, every hospital will run this learning algorithm that I mentioned, this idea of computing a prediction and updating the model a little bit based on the error, and then computing a new prediction for another sample, re-updating the model, and so on. Every hospital will run this process for a small but kind of set and decided amount of times locally. And so every hospital will reach, at the end of this process, a slightly different version of the long list of parameters that will be specific for each hospital, because the data for hospital 1 was different from the data for hospital 2, and therefore their training paths will have diverged a little bit. And importantly, because each hospital is training the models locally on their own data, this data is never shared with the rest of the world. It's never brought outside of the hospital. And then finally, after a given amount of steps, every hospital communicates back the new version of model parameters that they obtained after this local optimization. And now the server has a problem. They have 5 different versions of the same, of more or less the same model. Let's say they have 5 different versions of the same list of parameters. And the question is, how can we aggregate them, combine them, in order to obtain a new version that is sort of representative of everybody, but is a unique version? And federated averaging specifically solves this by doing the simplest thing that you can do, which is just taking an average. It's a weighted average, and you have to weight by the number of samples on each hospital. So it's not like a really, primary school computation, but it's not much further than that. So literally, and this is specific to federated averaging, but it's also common to, I would say, most of federated learning algorithms in general. So the idea here is every model trained locally. So the data for each hospital was never shared. It never left the hospital. The only thing that traveled back and forth is this long list of parameters for the model. And when the server receives different copies of this list of parameters, because each hospital reached their own different copy, the server does one big average of this. They obtain a new global model, and most of the time they send this global model back to the hospitals for an additional round of training. And then after a while, we will consider that the training is finished, and hopefully the model will have learned something and it will have converged to kind of a stable state. So I hope that I've demystified again a little bit federated learning. Really, we're just taking an average of the model parameters. And I think the difficult thing here is really to understand that the model parameters are numbers, but somehow these numbers allow you to make a prediction about individual samples. So if you're thinking maybe of a linear regression, the model parameters would be the slope and the intercept. So in a federated averaging approach, every hospital would be computing their own version of slope and intercept that is specific to their local data, and then sending it back to the central server, and the central server would do a huge average of all of the slopes, a huge average of all the intercepts, and this would be the global linear regression model at the end. With linear regression, it's a bit more complicated, but you get the idea. Okay, so importantly, federated learning has many limitations and challenges to overcome. The first, and I would argue maybe the most important one, is that a big chunk of the cost and effort of the whole learning process is pushed to the data providers. Because when you could centralize the data, then typically you would maybe centralize it in a research center that has maybe a supercomputer, a cluster or something. They have data scientists on site who are expert at data analysis and so on. Now none of this is possible in the federated learning context because data doesn't move. So all of a sudden, the hospital or the research center who is providing the data also needs to provide the computational infrastructure for training these machine learning models. So maybe they need to buy machines with GPUs, or not every hospital needs to set up a cluster, but still you need to provide some sort of infrastructure, which by the way also means that you need kind of to pay the people who will maintain it. You need to have let's say IT personnel who is willing to play the game and kind of help out with the inevitable problems there will be with the software and the firewalls and everything. And so it's a huge burden really on the data providers who are already tasked with the burden of generating and curating the data. And by the way, in federated learning, because you cannot access the data, it's not easy to verify, for example, that every center is following the same conventions, for data annotation or even the same protocols for data collection. And so it's really everything becomes a little bit abstract and it's really difficult, and you have to kind of all of this difficulty is placed on top of the data providers. So this is a big limitation. The second limitation, and this is more from the, I would say, the algorithmic side, is that it can actually be proven mathematically that if your distribution of data among the different clients is very heterogeneous, then your federated learning model will suffer a lot. It will be very difficult to train a model that is actually able to output meaningful predictions. And there's different types of heterogeneity. There's different reasons why it can be difficult, but just so you know that uh, data heterogeneity is, I would say, the number one killer of federated learning projects, at least from the algorithmic point of view. And then finally, and I will not say this enough today, federated learning is not a silver bullet that allows to... Sorry, one thing. Je suis un appel, désolé. D'accord, ça marche. Sorry. Federated learning is not a silver bullet that allows you to claim that you are 100% privacy preserving. On the other hand, you have to be really, really careful. And one of the main reasons for this is that it's still possible to reconstruct the training data from the final model with some caveats, and it's not actually so simple and so on. But in theory, it can be shown that under some conditions, it's possible to recover the training data. And I'm showing here some images because it's kind of visually striking, but it can be done with all types of data. And so it's not true, at least it's not 100% true, that the promise of federated learning was we only share aggregate level model parameters. We never share the raw data, therefore we are privacy preserving. This isn't fully true. You need more than that. But federated learning is kind of a necessary first step, and then you need to add stuff on top of this. And so for security specifically, in federated learning, it's a huge topic. It's probably the kind of the biggest topic. It's probably the biggest topic and so we distinguish many different kinds of attacks. So there's the obvious attack that I talked about, where somebody steals, maybe, somebody listens into the exchanges between a hospital and the central server and is able to steal the model that was locally trained only on that one hospital data for the first round. And this gives them a big advantage because that model was trained only on the one hospital data. And so they can try with some mathematical optimization techniques to extract the original training data for that hospital. So this is kind of the basic and most obvious and most talked about problem that you can have in federated learning. But there's also the idea of poisoning attacks. So some malicious centers who may participate in the federated learning scenario only to kind of make life harder for the others. And if you just blindly trust everybody, it can be very easy for them to, for example, share model parameters that don't make any sense, but that will kind of pollute the aggregation. So if all of the hospitals are sharing their own model parameters and one of the hospitals says, my model parameters are minus infinity for all values, then the aggregation at the end will fail basically, and they will have successfully poisoned the process. And finally, there's also the idea of free rider attacks. So these are institutions that participate in the federated learning process, but they contribute as little as possible, but they still reap all of the benefits at the end. And so for security, and specifically for this issue of reconstructing the training data, we have two techniques that are commonly talked about. One is called differential privacy. It's complicated, but the idea is simple. Let's add a little bit of noise in the training so that it's impossible to say whether a specific training sample was actually used during training or not. So the idea is, if I ask you your age, instead of telling me your exact age, you tell me your age plus or minus a random value, and you change it a little bit every time. And then there's a whole mathematical framework that allows to kind of say how many times I can ask you that question before I am able to kind of figure out your real age, because you are just adding random noise with zero mean. But so differential privacy is kind of the first idea. And the trade-off that we're talking about is that we're adding privacy by introducing differential privacy, but at the cost of decreasing the performance of the predictions of the final model, because we are adding noise during the training. And the second method that we talk about is secure aggregation. And the idea here is instead to use cryptographic techniques to sort of hide the model updates in a smart way. It's very complicated again, so that you can still have the aggregation results at the end in clear. So you are able to obtain the final aggregation value, but you are never able to look at the individual updates from each hospital. So this is very strong, but it's really, as I said, it's quite complicated, advanced mathematics that I don't understand at all. But here, the trade-off is instead with computational cost. So we're still adding privacy, but at the expense of computational cost, because we're adding these encryption and decryption and so on, which are typically more costly than simply just doing the operation that you wanted to do. Okay. So what are some example applications? Okay, so there's some papers that are specific to hemoglobinopathies, not that many. There's like, I don't know, maybe 5 when you look for federated learning and hemoglobinopathies. There is one paper that talks about diagnosis of beta thalassemia from, I think, lab results, if I remember correctly. But I didn't really like this paper because it was only what we call simulated federated learning. So they took a data set and they simply kind of decided to split it in a synthetic way among fake centers. So it's not really, I think, super interesting. It just shows that you can apply the algorithm. And then we have the Mosaic framework, which was developed in the context of some Horizon projects, Genomed for All, Syntema, and so on, that are where part of the Helios network is also participating. And in this case, I think it's a bit more interesting. There's first of all, so it's called Mosaic framework because it's not just one method, but it's a combination of different approaches. It's quite cool. You do some subtyping, and then you do some prediction and survival analysis and so on. So that's really nice. Plus, as far as I can tell, maybe not in the paper that introduces the method, but there's been some real world deployments of this kind of approach. So it's a bit more significant, I would say. So if you're interested in these kind of things, check out these papers. There's a long history of like very flashy deployments that have been done since the 2020. Especially in the beginning, a lot of industrial actors were eager to show that they were that they were able to do federated learning. So we had NVIDIA, we had Intel, we had a French US company called Substra, and they all kind of showed these very interesting deployments. They were interesting either because they were with a lot of different sites, So, the OpenFL, I think, is the biggest one to date with more than 70 hospitals from, well, all over the world, in theory. And it's a medical imaging task for segmenting glioblastoma. So that's really cool. And if I can plug in a little self-promotion, well, our software that we developed in my research team called FedBiomed was used by a German team for deploying federated learning on 8 different hospitals nationally. I mean, Germany is a federation, so yeah, we can say nationally in Germany, and just last year. So that was it was really cool for us. Federated analytics, as I said, there's been a lot of demonstrations of platforms, mostly during COVID, and the NIH and so on. They also have some sort of demo deployments of federated learning. I don't know how many of these are still alive today, let's say, but it's interesting. And I think in Europe we have a framework called Capana. Again, it's developed by some German research teams, and it's kind of similar idea, sort of doing analytics in a federated way. So it's pretty cool. And there's additional ways in which you can sort of develop or think about federated approaches that are not specifically federated learning. So we've talked about analytics, but there's also an idea of simply doing federated deployment of models. So the idea is we don't care about training, we don't care about the learning process, but we still want to be able to have a way that a researcher can come with a pre-trained machine learning model and simply ask a network of hospitals to conduct some evaluation on their own local data for that model. And so there's this framework called MedPerf, and it's kind of the state of the art in this scenario. And finally, a little bit, well, not finally, I think I have a few more slides, so I'll try to be very quick. There's these 2 big projects. Genomed for All, I think, just finished, and Syntema will finish soon, I think. And they deployed a federated platform that does a lot of things, among which federated learning and synthetic data generation and others. And so if you're, and it's specific to rare diseases. So if you are interested, check out these projects, and you can, I guess, ask to use their platform. I maybe I will go quickly. It's just, I think we have a lot of research that we do in our team. I just want to spotlight the FedBiomed framework, which is the software that we're using and developing for federated learning. And it's a open source software, and we're always looking for collaborations. So please get in touch with me or with anybody from the network. If you are interested to collaborate in a federated learning or a federated analytics way, we will be happy to support you. And I'm sorry to all the good research and students that did this very good work, but I think I will skip it. Just to say important take-home messages from today. So the 2 important preconditions for federated learning is you want to have a scientific collaboration, but you have some privacy preservation constraints. We've talked about, however, many challenges in federated learning, specifically that a lot of the effort is pushed to the hospitals and to the data providers who are already doing the effort of generating the data. It requires IT expertise on the hospital side, probably also some data science expertise, so it's not trivial at all. And it's not always easy to take your scientific workflow and just simply, do it in a federated way. Sometimes it can require a little bit of careful mathematics. But I also want to kind of state that in my personal experience, federated learning, when you go to the real world, is more of an organizational and engineering problem. So it's more about establishing the collaboration. It's more about agreeing on a common data standards and data model. It's more about actually having the technical skills on site to deploy the federated learning software and whatever. Um, so all of this goes to say, I think that I mean the federated learning part, when we think about the algorithm, it can be scary or strange, but it's not the most difficult part when you're actually trying to build up a collaboration. And importantly, remember that federated learning is not the silver bullet for privacy and security. So we talked about privacy risks, that the model, even though it's only aggregate data, can still leak some data. Actually, I think that in the latest interpretations of the AI Act and so on, even the models are kind of considered borderline sensitive information. So uh, kind of this may complicate things. And we talked about some measures to mitigate these issues, such as secure aggregation, differential privacy, and so on. Okay, so thank you. Sorry for running until the last second.
Thank you so much, Francesco. I have to say, even for me, I'm a biologist by training, I was able to follow. So thank you so much for this great talk.
Thank you.
Do we have any questions? We have a couple of minutes. Does anyone have any question? I mean, okay, we do. Sarah, do you want to go first?
Yeah, thank you very much for a really interesting talk. My name's Sarah Trumpet. I'm a haematologist from University College London and NHS Blood and Transplant. So when we're doing this kind of work, our biggest challenge is around the anonymization, because by sharing even small amounts of data, even if you're de-identifying a patient, by the nature of federated learning, you want usually unconsented cohorts. Therefore, you have to anonymize rather than de-identify. And in doing so, there are very strict rules, certainly where I'm based, around that process, such that if a patient might be identified by the virtue of their rare disease, then they cannot be included. And so what happens is that you get a lot of average patients in your cohort, and you actually lose the rare diseases because there's not enough of them to ensure that they're de-identified prior to sharing with the overall model in your federated model. And I wondered if you had any advice to, and then I worry that the overall model is just looking at Joe Bloggs. Well, I don't know what the equivalent of Joe Bloggs is in other languages, but just the average patient, and we lose that granularity and the finesse that particularly those of us looking after rare diseases are desperate for.
Yeah, so I mean, absolutely. This is definitely, I would say, a big issue. I think sometimes it can be possible to sort of mitigate with some algorithmic or some mathematical techniques. Although obviously the challenge that you are referring to, I guess, is strictly from a legislative point of view. And if you cannot include those patients, then it becomes really, really tough. The sort of the good experience that we've had, but it might just be because we've met the right people or whatever, is that sometimes we were able to build a case by saying, we're applying federated learning with secure aggregation, with all of these like overhead on top, and it allowed us to kind of push the bar a little bit and be able to include some of these rarer patients. But apart from that, yeah, I mean, I'd be happy to sort of discuss your situation more in detail, but I don't have any sort of a good answer for you off the top of my head. Sorry.
Thank you.
Thank you. Petrus?
Hi, thank you, Francesco. Very nice presentation. So my question is related to some of the steps that you need to do to design your federated analysis. So for instance, how you choose the right model to use, what kind of pre-processing you do and things like that. So I'm wondering how you can do it in a federated way or whether some centralization may be needed before you start employing your model in the different sites. Thanks.
So there's two classic strategies. There's three strategies. Either every center agrees to, like you said, centralize a little bit of their data, a small subset. This would be the ideal scenario, but it's not always possible and it's kind of difficult. Idea number two is typically in this kind of collaborations, you have one or two centers that are providing most of the data. And so these centers maybe also have sort of the data scientists in-house. So these centers are kind of leading this pre-phase of model selection and so on. And then you simply just blindly apply it to everybody. When you cannot do this, there's also the idea of using public data sets that are kind of similar to yours and hoping for the best. In general, it's a very complicated and very kind of nuanced issue. This is a little bit also where the idea of analytics comes in my opinion, because this initial step of simply having some federated way to explore your data can give you an idea of, are there some heterogeneity points? Are there some like difficulties that you foresee? If the data is more or less homogeneous and similar to, some public data, then maybe you can trust that public data. So this can help a little bit, but overall, when you're in the real world trying to design a federated analysis, it's one of the biggest challenges for sure. And related to this, one thing is the step after, that's debugging your model. So when your model doesn't work for specific samples, typically in a centralized setting, the first thing you do is you look at that sample, you try to look at a few of them and see if there are some patterns where your model always fails. This is all things that you cannot do in a federated way. So that's an additional kind of very, very tough complication to deal with.
Thank you.
Thank you. And then last two questions, Jan first.
Yes, thank you, Francesco. That was a really good talk because I have no idea about federated data and models and so on. From a purely practical point of view, is the system database agnostic in so much as if there's rather heterogeneous parameters between the data sets between centers? What I'm trying to say, I think, is from a practical point of view, if you already have some sort of data sets on your patients and you wish to submit it to a collaboration that's looking at federated learning, are there some things that we need to do to the database and the data in the database in order for it to be acceptable? This interoperability aspect, basically.
Yeah. So, sorry.
No, I was just going to say also, I think Sarah, she left. I can't see her anymore. It's also quite difficult when there are really, really rare cases. For example, you've got one or two patients that just have a rare disease that there are only a handful worldwide anyway. So, how do you address this too? But more importantly, at the moment, I'm interested in the first question. Thank you.
Yeah. So the short answer is that it's not database agnostic at all. Actually, it's super sensitive to differences in the database. And there's different kind of differences that will affect the federated learning process. You have the sort of differences in the data format. So if if you gave different semantics to your columns or whatever, this is going to really affect the model. So you need a very, very airtight process of data standardization in the beginning. And this is where the interoperability and common data model and all of these things come in. And then there's the statistical heterogeneity. I mean, even if you've done all this work of ensuring that your data is properly formatted and everything, it may be that your patients in Greece have a different distribution statistically than the patients in France. And so every time you do this local optimization, they will diverge. And it's not always true that when you aggregate them to something that's meaningful. Sometimes you aggregate them to something that just doesn't make sense at all. So it can really mess up your training, and it's something that you need to control. So the statistical part can be dealt with a little bit. The data formatting and everything is really something that you have to do. And this is one of the reasons why I said that a lot of the effort is shifted to the data providers.
Yeah.
Is because, yeah.
Yeah, and I'm just thinking, for example, in the lab I used to head up, we had data on thousands of patients, and not just hemoglobinopathy patients, lots of different groups of patients with rare diseases, and it would be really interesting if we could, contribute some of this data to, in multi-center efforts, basically, in order to mine interesting information from these data sets. And I'm just wondering if it's feasible to do something like that or not, and how it would be possible to go about it. But it's probably a massive task that needs some sort of serious funding up front.
Yeah, it's definitely a task that requires funding. I can say just one thing, and then maybe Marco, who is going to speak after me in any ways, he will maybe complement on that. But the promise and kind of the win that you get from it is that in theory, if you do it right, following the FAIR principles and everything, it's a one-time process, right? And then you have potentially infinite reuse of your data.
Okay. Thank you very much. Thank you.
Thank you for the bridging to my question. So you can hear me properly, right?
Yeah.
Yeah. Okay, great. So we've been listening, just so you know, we've been listening with the whole room here. I don't know if you can see that. I don't think we have a camera on. Is it my camera that is then? Can you see that? Yeah. So you see, this the biosemantics group is having its an internal hackathon today. We stepped out for your talk. It was excellent.
Wow,
I have two questions, and one maybe relates to what Jan suggested. Is that and one is about privacy preservation. Maybe it's even a question also for our Benzi friends here. And one is if you could elaborate on the vertical partitioning, and that relates to FAIR and some of the work that we do. On the privacy preservation, I'm always interested in so one thing we get taught on by some of our legal experts here at the hospital is responsible research more than 100% privacy preserving. And I'm curious if also some work is taking place on that to do it. Sometimes 100% is actually not in the interest of certain groups of patients, right? Who just can't wait for good results. So if there's also discussions going on in the federated learning community on what is responsible, what are acceptable risks to take, because there's benefits that are larger than the disadvantages, things like that. And maybe that is a question for the Benzi Foundation as well. And if not, maybe that's something we could look at. And for the federated learning, I think so. the work we do here is often multi-omics and building knowledge graphs. I think that's all related more to vertical partitioning than horizontal partitioning. And I would think also if you look at just what databases are out there, what is available for rare disease analysis, it's actually more vertically partitioned than horizontally partitioned. It takes a great effort to make sure we have enough quality data that is horizontally partitioned. So I was curious about the federated framework that you have, if you can say a bit more about how much is going on the vertical partitioning side. It don't have to be a long answer. It can also be, oh, that could be interesting to actually elaborate on or work on with and fill that niche with our group. So these are the two questions about privacy preservation and the vertical partitioning.
Yeah. So for responsible research part, it's the first time that I hear this concept, and I don't think it's sort of too much talked about in the context of federated learning. Although maybe one thing that relates to this a little bit, which is a very common and talked about topic in federated learning that I didn't touch on today, is how to assess the contribution of different samples to the learning process in order to kind of correctly give incentives for people to participate. So it's not, I guess, it's not exactly this idea of responsible research versus 100% privacy preserving, but it's still in the realm of kind of understanding what it means to contribute for a specific patient to use their data in a federated learning context, and how much that data contributes to the overall learning process. But yeah, so the short answer is that I'm not aware of any sort of discussion. Actually, obviously, I would say from the federated learning literature, everyone is trying to show that they are 100% privacy preserving, blah blah blah, because it's kind of the race to the top. And for the question about vertical, again, unfortunately it's not really my domain of expertise. FedBiomed barely supports it, I would say, but it's a very super interesting topic. I know that in its kind of basic form, it's really tied to sort of cryptographic verification that subject IDs are matched across different data sets. This is kind of, as far as I'm aware, the sort of the biggest challenge and kind of biggest talking point, research point in the vertical partitioning literature. I know that there are notions of federated knowledge graphs, but I'm also pretty sure that unless it's something really new, this hasn't been explored that much. And I think technologically and technically can be quite difficult, but it's definitely a very, very interesting topic to explore.
Okay, thank you. The way, just to elaborate what I know about this responsible research, what I understood from it, I'm not an expert, maybe Annalisa, etc., can explain this even better, is that basically the stakeholders sit together in a kind of workshop to define what is acceptable, what is reasonable, what is responsible research, taking everything into account. Also and including the patient representatives, who then also get to express where they stand. I think that's an interesting avenue to look into. It's nice to be privacy preserving, but if that means you die at the end of the week, then how much use is it, right? That I think that relates to it. I see Annalisa's hand is also up, so we're getting some expert input later on.
Yes, thank you so much, Marco, for letting me jumping in this in this discussion. So thank you so much, Francesco, for your kind overview of the federated learning. It was really interesting. What I would like to say is that I fully agree with what was shared by Marco, that it is more a matter of responsible research than being sure that it is 100% privacy preserving. What I was thinking is that also looking at the Federated Learning Training School, we can have a presentation or a brainstorming session on the GDPR and on the data protection with the key principles, in order to also increase the awareness about the provisions, the applicable provisions on that, considering that maybe we need to focus on the awareness of researchers on these topics.
Thank you, definitely.
Thank you, Annalisa. And lastly, Theo, I will ask a really brief question because we're 20 minutes late. Francesco, he's been talking for a while.
Sorry.
Hello, guys. I just jumped in before some time. I'm on the road. If I may say what Marco said before about responsible research, it may become out of the round robin, let's say, approach. And my question to Francesco is if he's aware of any AI tools regarding, let's say, the data sets verification or FAIR enabled on the one hand, and harmonization of the different data sets. Are you aware of any of that? Thank you.
The short answer is no. It's really difficult, I think, to develop such tools. There's obviously on the side of what you want to achieve, there's all of these data formats and like OMOP and so on that set a standard. But in terms of how you get to that standard, it's really, really complicated. And I think Marco is more the expert here on this topic. But I mean, I'm not aware of any sort of magic LLM or something that automatically verifies your data.
No, that would be too nice. Although people are looking into this, using AI, etc., to take you as far as you can get with verification. So that happens. So it's something we work on, obviously, and also with our colleagues now in Cyprus. And when we do FAIR, it's really to make this whole federated analytics. Then I guess it's the broader one that as much as possible can be automated, automatically finding the right resources, automatically accessing it under the right conditions, and then that the data is already interoperable, so that you can do the analysis and reusable. One of the examples that I often refer to when it comes to federated analysis, where at least the interoperability is done at source, is the work of André Dekker from the Mastro Clinic here. Often it is the personal health train. You can Google or find in PubMed publications about the personal health train. They do make the data fully interoperable at the source. And by that, they can run their federated algorithms, and they run all across the world. So that's one of the prime examples. We take it even a step further because we also want to automate the finding and the accessing, etc., of the data.
Great. Thank you, everyone. Thank you for the interesting discussion. Francesco, thank you once more. Just to remind everyone, Francesco is leader of Working Group 3 of Helios. So if you have any questions, any ideas about projects, please reach out to him. Thank you again, Francesco, for this great talk and everyone that contributed to the discussion.
Thank you, Janu.
Yeah, just one more thing.
Thank you.
I don't think I ever received the survey about AI that was sent out from Working Group 3.
That was a while ago.
Yeah, maybe it went into my trash. But anyway,
I will double check that.
Okay, fine. Thank you.
Thank you, everyone,
you.
for staying with us as well.
Thank you very much. Bye-bye.
Thank you. Bye.
Have a good
Thank you,
day.
everybody.
Bye-bye from all of us.
Bye.
Bye
Thank
to all of
you.
you.
Bye-bye.
Bye.
Bye.